Is about double replacement reactions. This topic is a little complicated, but you can do this. Take things one step at a time. Here are some of the terms that you will need to understand. You might want to jot down the definitions of these terms as the video proceeds. We're going to be talking about dissociation or dissociating, precipitate or precipitate, depending on how you want to say it. Strong, weak, and non-electrolytes. We'll introduce concepts of molecular equation, total ionic equation, and net ionic equation. And we'll talk about solubility, which compounds are soluble in water and which are insoluble in water. What happens when you dissolve a compound in water? It really depends on the compound. Many ionic compounds dissolve in water. They are said to be soluble. Sodium chloride is one of these. When it dissolves in water, as seen here, it dissociates into individual ions. These ions are mobile and are constantly moving throughout the solution. They are charged and mobile, which are the requirements for something to be an electrolyte. We call soluble ionic compounds strong electrolytes because they dissociate completely into ions when added to water. If I add 100 formula units of sodium chloride to water, I will get 100 sodium ions and 100 chloride ions. Some compounds only dissociate partially when dissolved in water. These are called weak electrolytes. And some compounds do not dissociate into ions at all. These are called non-electrolytes. Soluble ionic compounds are strong electrolytes, and so are the strong acids. The strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. You will need to memorize these strong acids because once you know the strong acids, then you know all the weak acids as well. The weak acids are just not the strong acids. Weak acids, along with ammonia, which is a weak base, are weak electrolytes. Then we have the non-electrolytes. Water, sugar, alcohols, basically do not dissociate into ions at all when they're dissolved. The one we'll be looking for today is water molecule. So let's take a look now at what a strong acid looks like in water. In this PhET simulation, we can look at the properties of strong and weak acids. When a strong acid is added to water, it dissociates completely. Here, our acid is generic and is composed of H plus and an anion. And an anion, I should say. In water, the H plus ion is very reactive, so it immediately gloms onto a water molecule to form hydronium ion. So if I add 100 strong acid molecules to water, I will end up with 100 anions and at least 100 hydronium ions. We can see this is a strong electrolyte by using a conductivity meter. When lowered into the solution, electrical current is carried by the charged ions and the light bulb glows brightly. We can contrast this with a weak acid. When our generic weak acid, HA, is added to water, most of it remains as HA molecules. Only a few anions and hydronium ions are present. So if I add 100 molecules of a weak acid to water, I will wind up with more than 90 molecules of what I started with and very few ions. If we use our conductivity meter again, we can see that the light glows, but it glows much less brightly. To sum up, strong electrolytes dissociate into ions completely in aqueous solutions. Very few molecules of a weak electrolyte will dissociate into ions when it is dissolved in water. And non-electrolytes essentially do not dissociate into ions at all. When we learned about double replacement reactions, we assumed that they occurred the way the equation was written, but certain conditions have to be met in order for these reactions to occur. There has to be an overall change in the composition of the solution. There are two ways this can happen. One of the products must either be an insoluble compound or a weak or non-electrolyte. The first possibility is that a solid or insoluble compound is formed in the reaction. Some ionic compounds are insoluble in water. If the ions that make up these insoluble compounds meet up, they begin to form a crystal, a solid. Once these crystals become large enough, they diffract light and the clear solution becomes cloudy. You will use solubility rules to determine which compounds are insoluble in water, but those are covered in another video. Let's take a look at a precipitation reaction. Both sodium carbonate and calcium chloride are soluble in water. If we combine them, we will form a solid. This solid is called a precipitate because it precipitates, or it's called a precipitate because it precipitates out of solution. But before we mix them, let's zoom in and see what's present in each of these solutions. Looking at the sodium carbonate solution, we see that there aren't any sodium carbonate crystals present. There are just individual sodium and carbonate ions floating around in solution. And if I could have learned how to use the animation software, they really would be floating around. But that's for another semester. Let's zoom in on the calcium chloride solution. We have calcium ions and chloride ions floating around in solution. When we combine these clear solutions, the mixture becomes cloudy and white. This is due to the formation of the calcium carbonate crystals. Let's look what is happening in this mixture now. As you can see, we have sodium ions and chloride ions swimming around in solution, and the calcium and carbonate have formed crystals. We're used to looking at chemical equations. Those are the equations that we've been looking at in the reaction types lab, and that you've gotten pretty good at balancing, I hope, by now. The chemical reaction would look like this. Sodium carbonate in an aqueous solution, or dissolved in water, will react with calcium chloride, aqueous, to form calcium carbonate, which is a solid, and sodium chloride. But if we want to know what's happening in this reaction, we can write this in a more detailed version. We call this the total ionic reaction. We started out with sodium ions and carbonate ions, and calcium ions and chloride ions. Once we mixed all that together, we ended up with calcium carbonate solid and still sodium ions and chloride ions. These calcium carbonate crystals form, and eventually they'll all fall down to the bottom of the solution. But right now, when you first mix them, it just makes the solution go cloudy. We can simplify this even more by taking out the ions that don't react. We call them spectator ions. In this reaction, sodium and chloride ions are the same on both sides of the equation. This gives us our net ionic equation, which says that carbonate ions and calcium ions will combine to form calcium carbonate. Now let's look at an example where there is no reaction. If I combine solutions of sodium hydroxide and potassium bromide, I do not get an overall reaction. Let's look at what is happening in these solutions before we mix them. In the first solution, we have sodium ions and hydroxide ions. In the second solution, we have potassium and bromide ions. We can predict this because they are both soluble ionic compounds. Now, let's combine these. When we combine them, we get a clear solution, no cloudiness, and there is no noticeable temperature change between the original solutions and the mixture. If we zoom in on our mixture, we can see that we have sodium, bromide, potassium, and hydroxide ions on solution. we can write the total ionic equation like this. If we cross out the ions that don't change, we cross out sodium, we cross out hydroxide, we cross out potassium, and we are left with nothing. We have no net ionic equation, and so instead we would write no reaction. Now let's look at another reaction. This one has a lithium acetate solution reacting with a solution of hydrogen iodide. Let's zoom in and look at what is going on in these solutions. Lithium acetate is an ionic compound that is soluble in water, so we have lithium ions and acetate ions floating around in solution. In the hydroiodic acid solution, we have iodine ions and hydronium ions. Remember that H+, as soon as it forms, gloms onto a water molecule to form H3O+. All right, so when these solutions are mixed, we end up with a clear solution. Looks the same as it did in the original test tubes, but the temperature rises quite a bit. It becomes uncomfortable to hold that if you were holding that in your hand. So let's zoom in and see what's going on in the mixture. Well, we still have lithium ions and we still have iodide ions, but we no longer have hydronium ions or acetate ions. I didn't even put any in this picture. What we have now are lots of acetic acid molecules. Acetic acid is a weak acid and it barely dissociates into ions. So looking at the total ionic reaction here, we can eliminate the spectator ions, and that would be lithium and iodide. Lithium and iodide. And we come up with a net ionic reaction that is shown here. Acetate ions will react with hydrogen ions to form acetic acid. But because this is a weak acid, there always are some ions present. And so it would be a little more correct to actually put a double-headed arrow in here. All right, one last reaction. Here, we're going to work with solutions of sodium hydroxide and hydrochloric acid. Once again, let's zoom in on these solutions and see what's present. We have sodium ions and hydroxide ions. And in the other solution, we have chloride ions and hydronium ions. Okay? When we mix these together, once again, we get a clear solution that looks just like what we started with, but the temperature has risen quite a bit. All right, if we zoom in on that mixture, we can see we still have sodium ions and we still have chloride ions. But now we no longer have hydronium ions or hydroxide ions, we have water molecules. So our net ionic reaction, once we get rid of these spectator ions, looks like this. So we have hydroxide ions plus hydrogen ions going to form water. Remember, water is a non-electrolyte for all intents and purposes. So it's going to form molecules. And once those molecules are formed, they do not dissociate into ions to any significant extent. So in summary, double replacement reactions take place when a precipitate is formed or when a weak or non-electrolyte is formed, and there must be a net ionic reaction.